Welcome back, everybody, and welcome to a new week. The topic this week is to continue our discussion of time-independent perturbation theory. And we're also going to look at several examples of contributions to perturbation theory. This will be on the whiteboard notes. And we are going to link this with what we have done earlier in connection with full configuration interaction theory. So the first part of the lecture is going to be roughly 10-15 minutes of a reminder of what we did last week, some of the basic definitions. And then we are going to look into more detail into Rayleigh-Schrödinger perturbation theory and what's also called Bruyne-Wigner perturbation theory. And we will continue with this tomorrow. We will go through several examples, and we will also introduce diagram rules, because this becomes extremely handy when we do perturbation theory. So I'm going to mainly use the whiteboard today, and let's now switch back to that one. So stop sharing here and move over to the whiteboard. And please feel free to put questions in the chat and in case something is unclear. So what I want to do first is to remind you quickly about what we did last time. So the questions which we looked at last time were defined by the wave function as an expansion in terms of a series of Slater determinants. So let's just put up as a header MBPT, so which is many-body perturbation theory. And the starting point was us. So this is roughly just a reminder of what we did last week, and I'm going to set up the equations which we ended up with last time. So if we now single out the ground state, you could actually do this for other states than just a ground state, but we often, if we are now looking at what we call a system which is often called a closed system, I mean a closed field particle orbits up to the Fermi level, where we have essentially one Slater determinant which we can use as an ansatz. What we had then was an ansatz for the ground state, which is given by this state phi 0. So that could be a Slater determinant if we want to. And then what we did when we looked at the full configuration interaction theory and also Hartree-Fock theory, we made an expansion or reordering of all these linear combinations of Slater determinants, which are defined by our computational basis in terms of various particle-hole excitations. So I'm just setting up these expressions to remind you quickly of what we did previously. And IJ, AB, plus, and then we have a series of other contributions like 3-particle 3-hole, 4-particle 4-hole. And then I'm just going to write the final one as an NP-NH, which means that the last possibility is the set of all n-particle n-hole excitations. Now, what we did last time was also to rewrite this in a more compact form. So we simply rewrote this as the ansatz for the ground state. This is our new vacuum reference state, plus just a linear combination of Slater determinants, where we then have these coefficients Ci, and the i's are now different, so we should in principle use another symbol. So let's just introduce a Greek symbol here. So this runs from lambda equal 1 and in principle to infinity. And this is the overlap between the exact state and the states which we are expanding in terms of. So this is just another way of rewriting the first equations which we have here. Then what we looked at was obviously the eigenvalue problem, where we now have the eigenvalue problem with a Hamiltonian, which is given in terms of a unperturbed or non-interacting. So we will often call the non-interacting case as the unperturbed one, because we're going to treat the interaction as a perturbation. And as we discussed last time, for a very simple example with a two-level system, we could actually then see what were the kind of criteria for a Taylor expansion of the square root for the problem when we solved the 2x2 eigenvalue problem. Then to expand that square root, we needed to have a specific ratio between the energy differences between the states and the strength of the interaction. Now, what we did then, and this is essentially what we did when we did the FCI calculations, we would multiply from the left with phi 0, and then we have same eigenvalue problem, and this gave us then simply phi 0 of H0 plus, sorry, this should not be phi 0, this should be psi 0. So this is psi 0, that's the exact state. And then we have plus H of I, and then we have psi 0 here. Now, if we look at the last term, this is a term which we rewrote in terms of the phi 0 term, and we made also an assumption that we could define something which we call for intermediate normalization. So let's set up these definitions which we used last time. So I'm just going to switch slide here, if that is okay. So one of the things which we also did last time was to remind ourselves about the unperturbed energy. So this is an uppercase letter epsilon. And this quantity was now given by the expectation value of one part of the Hamiltonian, the so-called non-interacting part of the Hamiltonian. And we know that this quantity here is a quantity which we then can rewrite if we made this assumption about intermediate normalization, which simply means that we reshuffle the strength of the coefficients in front of the wave function expansion. And what we did then was simply to assume that we can define this one to be equal to 1. That means that this constant C0 drops out of the equation since it's just equal to 1. Now, when we did that, if we look at this equation which we have here, this equation here, and if we go back to what we have here, then we know that since we have H0 acting on phi 0 equal to this epsilon 0 times phi 0. So when I now multiply psi 0 here with this term here, this is due to the fact that we have also assumed that these are emission operators. We have a psi 0 complex conjugate, and this is equal to epsilon 0. Now, why do we do this? Now, one of the reasons for that is that if we look back at the equation which we had, let me just quickly go back, and then we go back to this page, because in my previous page, what I did was simply to write this phi 0, which will be multiplied from the left here. Then I have phi 0, H0, and psi 0. And due to the fact that we are using this intermediate normalization, then this term here can then be simply rewritten in terms of epsilon 0. And then what we did was to define the correlation energy. So this is the correlation energy. And this differs from what we had in full configuration interaction theory. So I'm just going to repeat some of the things we went through last time. So this E0, which we have here, is actually the exact energy of the ground state. And that is the same as H acting the full Hamiltonian, acting on this state. So that gives us this equation. And this should be a psi 0. And this term which we have here, this epsilon 0, which we defined above, is the quantity which now will define the correlation energy. And this is a little bit different from what we had in full configuration interaction theory, because in full configuration interaction theory, what we did was to subtract from that one the total reference energy. So let me very quickly remind you of that before we move on. So if we now look at the full configuration interaction theory, which we have been discussing previously, then the energy of the system is given by, so the correlation energy, and we are going to put FCI here to distinguish these two quantities. That is still given by E0, but then it has E0 for the reference state. And just to quickly remind you of that, this E0 for the reference state is a quantity which we defined as the expectation value of the full Hamiltonian, but with respect to the ansatz for the ground state. We are not limited to the ground state, but it's normal to look at the correlation energy with respect to the ground state problem. And we know that this last term which we have, this delta E, FCI, is something which we then could write out in terms of an analytical expression in case we had performed the diagonalization, because the diagonalization gave us these coefficients CIA. So these are the coefficients of the eigenvectors from the exact diagonalization. And then we had an A of this operator F, which we called also the Hartree-Fock operator. This quantity which you see here is simply not this one, but this matrix element or integral. This is given by the overlap between phi IA with the Hamiltonian multiplied with phi 0. So when we calculate this transition for many body states, what this does is that it reduces just a summation over single particle states. And that is due to the fact that we keep this wave function, many body wave function, which is built up upon single particle wave functions. And we have always assumed that this single particle basis is an orthogonal and normalized basis. And then we had, in case we had a two-body interaction at most, then this translates into another integral, V of ij here, for anti-symmetrized. And this second term, which you see here, is actually the overlap between a two-particle, two-hole excitation, the Hamiltonian of the system, and obviously the ansatz for the ground state. So when we perform a calculation of the type of the FCI type of calculations, then these terms are actually given by the eigenvectors which result from the diagonalization. Now, in a certain sense, when you have these eigenvectors, it's actually a waste of CPU cycles to calculate these terms, because you do actually get E0. And then you can always define the reference energy. So this is just a quick reminder of some of the basic elements which we looked at last time. And if we just put labels into here, so this is a one particle, one hole excitation. This is this state. And this state then represents the transition from a zero particle, zero hole state to a two particle, two hole state. So that's the overlap between the states which we can produce when the interaction acts on the ground state, which then has to produce a two particle, two hole state in order to have a non-zero overlap between the states. Okay, so the other thing which we did last time was also to define projection operators. Now we are going to assume that we have a non-degenerate ground state. So there's only one ground state for the system. And this is our Slater determinant, which we use as an ansatz. That means that we could define a projection operator, which now, when it acts on the exact wave function, it projects out this ansatz for the ground state. So we define this projection operator, P, which is then simply given by the outer product of phi 0. Then this defines what we in perturbation theory often call an effective Hilbert space, or just a model space. So you will see these being used as synonyma, or what we would call an effective Hilbert space. And those are the degrees of freedom which we are normally interested in studying. That means that the remaining degrees of freedom will then be taken care of by a new operator, which is simply the sum over all the other states. And in principle, this summation should go to infinity because we have an infinite basis, but we will always truncate it, as we started discussing in the very, very beginning here during the semester, the first weeks of the semester. And These operators are so-called idempotent operators, as we discussed last time. So that means that p squared is equal to p. We also have that q squared is equal to q. Since they represent different states, it obviously follows that p times q or q times p has to be equal to 0. And that means also that these two guys commute. So that is equal to 0. And then these quantities commute also with a full Hamiltonian. So, but we have H0 is equal to Q of H0. Now let's put hats on them, and that is also equal to 0. Now, what we did last time when we had defined these different quantities was that we could actually rewrite. So I'm just repeating from last time. And this ends roughly the repetition from last week. From last week, what we could find then is an expansion of the exact wave function in terms of these different operators. We have n0 with a, in principle, a summation to infinity. So we have this operator q. Let me quickly remind you of some of these quantities. So we have H0, which is the non-interacting system, minus E0, which now contains the exact energy, plus the interaction piece. And this is to the power of n multiplied with phi 0. So this is the expression for the wave function. And that means that the elements which you see in here, they are normally called the wave operator. So in principle, what we did then was to use an iterative scheme to re-express this one in terms of something which acts on the ansatz which we have. Now, these equations here were obtained by introducing a kind of not fudge factor, but a constant here, which we are going to define now. And that is going to lead to two different types of many-body perturbation theory. Now, this expression which you have here is a little bit compact because in principle, what we have here is actually Q multiplied with omega minus H0. So H0 represents a matrix then, because we are always going to operate with a finite basis. And this could also be written out as Q omega, since H0 commutes with Q. And we often write it in a sloppy way like this. So keep in mind that what we have then is in principle, since we have that Q squared is equal to Q, we could have written it like this, which would be more mathematically correct. But then we end up with this kind of compact notation. So just keep in mind that what we're having now is an operator here, which has to be inverted. So it leads to a matrix, since we will always deal with a finite excluded space. That means that this H0 is going to act when you now perform a Taylor expansion of it. So the Taylor expansion of 1 divided by omega minus H0. This quantity is, by the way, called the resolvent. And when this acts on the operator Q, then we know that H0 with Q commutes. So we can write everything either like this or in a more compact way like this. So these are just some kind of notations which we introduced last time. So in principle then, if we now write it like the way which we have in psi 0, the way you should read is Q divided by omega minus H0. This is the same as a sum over all the states from 1 to infinity. And we start the summation from lambda equals 1, simply because we have a model space or an effective Hilbert space which contains only one state, the ground state. There is nothing which hinders us setting up an effective Hilbert space which contains more than one state. But we are going mainly now in this course, we are going to target the ground state of a system. However, you could use this to look at the effective Hamiltonians, which act in an enlarged space. So this operator which we have here is in principle the same as us having these states lambda. So we are setting up the outer products of lambda divided by this omega minus H0. Now, since H0 will act on the state phi lambda, we should also keep in mind that H0 acting on phi lambda is going to give us a many-body energy for the non-interacting case, which is simply given by these eigenvalues epsilon lambda. So in our case, we have made the assumption that this phi's, the basis which we have, is an eigenbasis of the non-interacting Hamiltonian. Then what we could do is actually to multiply this equation here from the left with phi 0 times hi. If we do that, then we could actually calculate, because in many-body perturbation theory, this delta E, which is delta E0, which is the same as E0 minus epsilon 0, this is nothing but this expression which we have here, of h of I multiplied with the exact wave function. So now we have an expression for the exact wave function as a perturbative expansion. So that means that this quantity which we see here can then be written out as a sum over all these perturbative terms, n equals 0 to, in principle, infinity. And then we have a phi 0 with an h of I. So everything is now expressed in terms of the interaction. And this is what we are going to use when we are going to make the expansion. So this is going to be an expansion in terms of the energies and the interacting part of the Hamiltonian. So we have omega minus H0, and then we have omega minus E0 plus this H of I, and this term is to the power of n multiplied with phi 0. So this is the expression which we now are going to look at more closely. So what we have is, as we discussed last time, we have two types of perturbative expansions. One is named after the physicist Brieux and Wigner, who was also a mathematical physicist. And in this case, we have what is called Brieux-Wigner perturbation theory, or as we will just write it with an acronym, BWPT. In that specific case, we choose this variable omega to be equal to E0, the exact energy. And as we said last time and looked at last time, this means that we are going to get an expansion in terms of an unknown quantity, because E0 is actually unknown to us. And we are going to see what kind of consequences that has. And one of the consequences is that the favorite many-body perturbation theory expansion is something which is normally called Rayleigh-Schrödinger perturbation theory. This is Rayleigh-Schrödinger. Let me just write correctly here. PT. And this is something which we will just label as RSPT. And in that case, this omega is given by epsilon 0. This is going to give us a perturbative expansion where every term in the expansion has only known quantities. Now, the drawback with perturbation theory is that we don't know a priori whether the perturbative expansion will converge or not. So this is often something which one has to play around with in order to find whether the expansion seemingly converges or not. But that is still no guarantee, because there may be high order terms which could explode. So let's look at the Brieux-Wigner perturbation theory and write down the equations. And what we are going to do now is to link the equations with what we did last week with a simple model, which was a two-level model, which led to a 2x2 matrix which we could diagonalize exactly and get analytical solutions for. And then we're going to see whether Brieux-Wigner perturbation theory with that simple example gives us the exact result or not. So let's now look at Brieux-Wigner perturbation theory. So what that means is that the correlation energy, which we have, delta E0, is equal to the exact energy minus the non-interacting energy, which is a known quantity. And this is now given by a sum from n equals 0 to infinity. And then we have phi 0. And then we have the interaction part of the Hamiltonian acting on Q divided by omega. No, sorry, E0, not omega, but E0 minus H0. And this is now multiplied with the Hamiltonian. This is to the power of n, and then it's multiplied, it acts on, and finally on the phi 0 state, the ansatz. Now, if we write this out, we are going to get terms order by order, and they're going to look like this. So we're going to have a phi 0, and then the overlap between phi 0 and phi 0. This is a term which we are going to call first order in the interaction in h of I. And you see now that if I am going to take this term here and switch it over to the left-hand side here, then I'm going to have epsilon 0 plus this term, and that is the correlation energy which we had in FCI calculation. So E0 minus plus this term here gives us the reference energy. But then we have high order terms. So we are going to get something which looks like this, phi 0, and then we have an interaction piece. We have Q of E0 minus the non-interacting part of the Hamiltonian multiplied with h of I times phi 0. So this term which we see here is a term which we are going to call second order because it appears, the hi appears twice. And then it's pretty straightforward to see that we can add more and more terms. And so let's do that. So you will get then additional terms. And if we now stop at third order, just to illustrate the equations which we get, so we get plus, and then we have a phi 0, and then an h of I, or Q of E0 minus h of 0 times hi. So I'm trying to put hats on everything here. So sometimes I forget it, and you have to excuse me for that. And this just continues to infinite order. So the equation which you see here, this one, would then be what we would call third order in the interaction. And you see that you have two energy denominators. You have three terms for the which represent the interaction energy. And then that means that you have energy squared in the denominator and energy cubed in the numerator. And that gives a term which has the right dimension, which is energy. Now, there's a very useful relation here, which we are going to use now in order to rewrite this equation, because Brieux-Wigner perturbation theory can actually be summed to infinite order. The only problem is that, as you can see here, this term is actually unknown. But we can sum this sum by using a matrix relation. So let's just look at this useful matrix relation. So this is often one of these kind of hidden gems in linear algebra. So let's look at this linear algebra relation. Useful linear algebra relation. And this is something which probably you have seen, but if not, this is actually a very useful relation when you're looking at is in particular this type of series. So what we are going to do now is very much the same which you would do when you look at the T matrix in quantum field theory. The only difference between what we are doing and quantum field theory is that in quantum field theory, when this now translates into integrations over all the states which the system can reach, there is no limitation. Here we are limiting the states to those which are not included in the effective Hilbert space. So when you do quantum field theory, it's essentially the same type of relation which we are going to use. Now, another thing which is important is that we are assuming that this inverse exists. Okay. Now, this is an equation which we can write out as the inverse of the matrix A. So these are, in our case, they are, for all practical means, they are going to be matrices. Okay. So this is given by plus A minus, and then we have multiplied with B, and then we have A minus B inverse. So how can we see that this is correct? So in order to see that it is correct, so we're assuming that the inverse exists, we simply multiply from the right. So multiply from the right. And we're going to multiply from the right with a term which is A minus B. Now that means that if I do that, here I will obviously get just the identity. And on the right-hand side, what I'm going to get then is an A inverse multiplied with A minus B. And then I'm going to get plus, and then I have A inverse times B. And then the A minus B inverse is obviously taken out by A minus B. In principle, we should have an identity multiplied here. And now you see that this actually becomes equal to the identity, because when I take and multiply A inverse with A, that gives me the identity. I'm assuming that these are orthogonal matrices, and that is a very important aspect, or unitary, could be unitary matrices. And we have an expression here, A minus multiplied with B, which is this one, which then simply cancels this one. So this is just one way to show this relation here. Now, what we are going to do now is simply to, if you now look at these terms here, we are going to rewrite them in terms of this equation here from linear algebra. And then we're going to see that we can sum up everything to infinite order. So that means that we are now going to rewrite this in terms of something which can be manipulated with this expression here, or this linear algebra relation. So what I will do then is to define first a new quantity. So I'm going to show now that if I define E, so this is the same as E0 minus H0. And if I then look at Q multiplied with this quantity E minus, and now keep in mind that I'm just looking at the expressions because this is a matrix which then will be defined by the excluded space. So I'm simply going to plug in this quantity here, which is the interaction. So that means that what I will have in the denominator is actually something which I could write out as Q here, and then I have Q, and in principle, since this acts only on the excluded space, this would be E0 minus the Hamiltonian itself. But let's keep it like this. Now, if you now look at this expression here, I can now use that relation which I set up, because then if you use that relation, so if we now write this out and using that relation, or looking at the perturbative expansion, what we can do then is to rewrite this one as a Q of 1 over E plus, and then I have a 1 over E times Q times H over I times Q times 1 over E plus 1 over E of Q of HI of Q, 1 over E, and now I'm a little bit sloppy with the operator signs here. So this is also multiplied with Q here, and then 1 over E. And this just goes on to infinite order, cubed. So now I've been using that specific relation. And this means now that I can actually, when I sum this up, I can actually use that relation which you saw here and simply rewrite this in terms of a much more compact expression. So if I now do this, I can actually rewrite this in terms of delta E0, which is equal to phi 0, as we have defined, of h of I multiplied with psi 0. And this is a quantity now which is equal to phi 0. So I have the first order term, h of I times phi 0. But plus, if I now look at all these different terms in which I can sum up using that operator relation, so I would then have a phi 0 multiplied with h over I, and this is multiplied with Q, and then E0 minus H0 of minus of Q times H of I multiplied with Q here, and then this is multiplied with Q of H of I, and finally multiplied with the final term, which is then just phi 0. So this is actually the equation which we can then set up. So if I look at the wave operator itself, I can actually, with Brane-Wigner perturbation theory, I can write my wave operator as 1 here, plus, and then I have Q multiplied, and I'm going to write it a little bit more compact way here, E0 minus H0 minus Q of H of I of Q. And this is multiplied with Q and H of I multiplied with phi 0. So what I have now is an expansion which I can set up for the true wave function. And this expansion here is now possible since we are using Brane-Wigner perturbation theory. This is in principle very similar to what you would be doing if you're looking at the T matrix. So the expression for the T matrix would be calculated, or is normally calculated, with a similar trick as we use to obtain the expression which you see here. There will be a first order term, and then we have something which then can be represented in some cases with a geometric series. Okay, so what we are going to do now is simply to remind ourselves about the simple example which we discussed last week. So to illustrate this, let us now look at these expressions and apply them to a simpler case. So what we did last week, and let me quickly remind you of that, we had a very simple example, which was a two-level system. So we had a Hamiltonian which contained a non-interacting piece, where we now have only two single particle states. And so it has, everyone had an energy epsilon p, and then we had an AP dagger AP, and then we had an interaction piece, which was given by just a constant multiplied with the sum over all the possible states. In our case, these are just two states of AQ. What we also did was to define an unperturbed state, which we could call for phi 0, which we labeled as 1. And that is the same as an A1 dagger acting on the vacuum. And then we had an excited state, because we assumed then that this energy, the non-interacting energy for this state, was larger than the one from the state 1. And when we did the calculations then, what we had assumed is that H0 acting on any of these states, phi 0, is then given by this epsilon 1 times phi 0. And then we have an H0 acting on phi 1, which is actually state 2. That gave us an epsilon 2 times phi 1. And we made also the assumption that epsilon1 is lower than epsilon2. Then with these kind of ansatses, we could then calculate the expectation value or the transition or overlap of the interaction piece. And what we found then, and I'm just going to quickly set up the matrix, the Hamiltonian matrix, but let me just quickly remind you one of these calculations when I took h of I with phi1 here, then this was simply given by this constant g. And similarly, when I now took the whole Hamiltonian, I got diagonal elements. So this is the whole Hamiltonian. I got diagonal elements, which were epsilon1 plus this constant g. And similarly, when I took the state, the non-interacting state, which represents the second single particle energy, or could be a many-body energy, actually. Then what we got was a Hamiltonian matrix, which led to a typical eigenvalue problem. So we simply had a matrix A, which we then could define as epsilon1 plus g minus lambda times g, and then we have g, and then epsilon2 plus g minus lambda. And then obviously the equation which leads to the characteristic polynomial is the equation where we require that the determinant is equal to 0. Now let's look at Breen-Wigner perturbation theory. So what we're going to do now is to simply use this model, because you can see that we have calculated these terms. We have only two states. So in our specific case, the operator P, the projection operator for the ground state, is going to be defined by the outer product of phi 0. And the operator Q is going to be defined by the corresponding outer product of the state phi 1. So what we want to do now is simply to go back to the equation for Breen-Wigner perturbation theory and see what we get. So let's plug in things in that equation which we had. So if we now take the expression for delta E0, which is given by E0, which is the ground state of the system, minus epsilon 1. So epsilon 1 is this non-interacting energy which we have defined. This is going to be equal to the first order term, which obviously will be phi 0 with the interaction. And in our case, this is simply equal to g. And then I have a next term, which is now given by, when I now calculate the energy, there's going to be a phi 0, and then I have an h of I. Now, the only intermediate state which I can get is phi 1. So I'm going to get a phi 1 here. So this is the first part which you see here is the operator Q, so which we now have inserted because it's just given by one state. Now this operator Q, when I now have setting up the energy denominator, this is simply going to be given by E0 minus epsilon 2 minus g, and it's then multiplied by phi 1, and then we are setting up the operator Q again. So this is the new Q operator which we have, and this is then multiplied with h of I, and multiplied finally with, or acting on the state phi 0. And we know that this one is just given by this constant g. So if I plug in all the expressions here, so I will move this term to the other side. So let's do that before we take a small break. So what we're going to get then when we plug in the expressions is that we have E0 minus epsilon 1 minus g. And this is going to be equal to g squared of E0 minus epsilon 2 minus g. Now I multiply away, and then I put g squared to the right-hand side. So I can rewrite this equation here as minus epsilon 1 minus g and E0 minus epsilon 2 minus g squared equal to 0. And if I now replace in the equation I had for the determinant of A, with E0 with lambda. This is the same, if I do that, this equation here is equivalent with setting the determinant of A equal to 0, which is equivalent. So what we see now is that the Wigner perturbation theory for this simple example gives us exactly what we get when we have two states, which I would get when I set up the exact eigenvalue problem. So which is equivalent with us requiring that we have to solve this equation here. So the determinant of A, and A is then given by that matrix which you saw. So if we go quickly back here, the matrix A is simply this matrix which now defines the solution of the eigenvalue problem by finding the roots of the characteristic polynomial. And what we did now with Wigner perturbation theory for this specific case, which is a simpler case, is to show that doing Wigner perturbation theory is equivalent with solving the exact problem. And you can see now, and this motivates what we're going to do after the break, you can see now that we have a dependence on the exact energy. And if you do a perturbative expansion in terms of something which is unknown, we don't know that one, this is to a pretty good extent something which we would like to circumvent. And this is why we, after the break, we are going to look at the other formulation of perturbation theory, many-body perturbation theory, and that is Rayleigh-Schrödinger perturbation theory. So the thing which we want to do now, since the equations which we derived for Wigner perturbation theory do all depend on the exact energy. So we would have a perturbative expansion, or essentially it's a Taylor expansion, in terms of the exact energy. So the question now is whether we can circumvent that and simply re-express everything in terms of a Taylor expansion, which is going to be our many-body perturbative expansion, where every term is something which we know exactly how to calculate. So since I mentioned this, there is an obvious answer, and that obvious answer is Rayleigh-Schrödinger perturbation theory. So let's take a look at the basic mathematics of Rayleigh-Schrödinger perturbation theory. And so we're going to switch page and simply just set up our SPT, which stands for Rayleigh-Schrödinger perturbation theory. And in this specific case, what we have done is simply to define this parameter omega, which we introduced last week, to be equal to the unperturbed energy or non-interacting energy. So I will often switch between the naming unperturbed or non-interacting. If we do that, then the expression for the correlation energy for the ground state is then obviously given in terms of the exact energy minus the unperturbed or non-interacting energy. And this takes now a slightly different form, which goes from n equal to 0 to infinity. And then I have phi 0. And this is then multiplied again with the interaction. So now we're just looking at the energy. But now we have this operator Q, and this is now divided by, or we take the inverse of this matrix, and this is something which we can calculate easily. But now we have an H. Let's try to keep this other way of writing the Hamiltonian. But then we get, in the expansion here, something which is unknown for us, which is delta E 0. Now what we're going to do now is to regroup all these delta E 0 terms in terms of different orders of perturbation theory. So this is to the power of n, and it's multiplied with phi 0. So when I write this out, there is something we should keep in mind. And if we now set up these terms, there will be a term which will act on phi 0, which is given by this constant. So delta E0 is nothing but a constant. It's a scalar. It's just the difference in energy between the exact ground state and the non-interacting system. So if you now look at terms in this expansion which will contain this quantity. We are going to have Q multiplied with a constant acting on phi 0. So let's just take a quick look at that one, because this is going to simplify a little bit the terms which we are going to get. So if we now look at this operator Q multiplied with delta E0 and then acting on phi 0, obviously since delta E0 is just a constant, we can rewrite this as Q acting on phi 0. Now Q contains now all the states which are not contained in our effective input space or model space. So this is simply given by I equal 1 to infinity, and then we have a phi of I multiplied with phi of I. And we know that the basis we have chosen is an orthonormal basis. So this simply gives us delta ij. And that means that this contribution here is exactly equal to 0. Okay, so with that, we can start writing out this expansion, which we have here, term by term. And let's do that. So the first term is going to be pretty simple because this is the n equals 0 term. And that is going to give us what we will identify as just first order in the expansion. So if we now write this out, we will find that delta E can then be written as follows. So we're going to have the first term, which is the same as we got when we looked at Brane-Wigner perturbation theory. And this is something which is easily calculated. We often have pretty simple expressions for that, which we saw earlier. So just to remind you, this term here is actually us. If we have a Slater determinant, then this is just going to be given by the integrals over all states below the Fermi level. And this is going to be given by both the direct term and the exchange term. So we put this anti-symmetrization sign. So this is a term which we have already calculated and which in FCI calculations is always included in the definition of the reference energy. But here, this becomes our term to first order in the interaction. So this is something which we can calculate. Then we have the next term. And due to the fact that we have this minus delta E0 with the operator Q acting on phi 0, the term to second order in the interaction is actually going to be much, much simpler than what we had with the Brane-Wigner perturbation theory. It looks like that one, but now we have H0, epsilon 0, which is a known quantity, whereas in Brane-Wigner perturbation theory, we had the exact energy. So in principle here, and we should actually have, and I'm going to just put a delta E0, and this acts on phi 0. But then we know that this term, which we have here, this term, together with that one, is just equal to 0. So that means that to second order, we don't have this delta E0 term. Now, when we go to higher orders, then this is no longer going to be the case. So if I go to, so if we just remind ourselves that this is to second order in the interaction. If we then look at the third order term, what we are going to have then is I0, and then we have H of I, and the operator Q times epsilon 0 minus H0, and then we have the interaction piece, but now we need to take care of delta E0. And this is multiplied in turn with the Q divided by epsilon 0 minus H0. And finally, this is multiplied with H of I and phi 0. Then we have fourth order terms, etc., etc. In principle, this goes to infinity. The hope is obviously that we can truncate the many-body perturbation expansion, or this specific Taylor expansion, in terms of terms, perhaps at most to third order. we have no guarantee that the order by order terms may lead to convergence. In some cases, you may actually have to sum to infinite order. And this is the same as solving the full many-body problem. However, the hope is that we could truncate this expansion, let's say at second order, or perhaps at most at third order, because that will give us a set of terms which we can actually evaluate without too many complications. And actually, the second midterm is going to deal with the perturbation theory to a given order. And you will then see that you can actually evaluate many of these terms easily, or not exactly easily, but the interaction which you will get in the second midterm is one which will simplify the calculations of many of the terms which arise. So let's now look at these equations in more detail, because what we could do now is to try to regroup them a little bit. So let's regroup. And we are going to regroup in terms of this function or this parameter delta epsilon, the correlation energy. So we are going to rewrite delta E0 as a sum from I equal 1 in principle to infinity, but obviously we want to be able to truncate it. And then we have a term to given orders of the interaction. So if I look at my delta E0 for first order, this is something which we can calculate directly, and we have already done it many, many times. If I look at my delta E0, and now I'm going to make a simplification here, delta E0 to second order, and I'm going to make a small simplification. I'm going to just introduce a quantity which I will call for E0, which is the same as the non-interacting energy minus the Hamiltonian for the non-interacting case. So this is E0. So the second order term is going to look like as a phi 0, and then I have my h of I multiplied with q divided by this E0. So we should put operators on it, operator hats, and then I have h of I multiplied with phi 0. So this is our term to second order in the interaction. And then after we've gone through these calculations here, setting up the various expressions, we're actually going to now look at specific contributions to the energy order by order. So if we then look at the third order term, we will get a delta E0 to third order. And in that particular case, what we have now is a term which goes like, and now I'm going to use a little bit more compact notation. So let me introduce that one, because else I'm going to go crazy with all these terms. So I have a phi 0, and then I have h of I, then I have a series of operators, and then I have an h of I here, multiplied with phi 0. I'm going simply to write this one as h of I, and then I have all these things in the middle here, like this. So this is just a shorthand which I'm going to use. And now I can actually write this one as a term h of I, and this is multiplied with q divided by this E0. And then I have a new interaction because this is to third order. So we have q divided by E0, and then multiplied with h of I. And this obviously acts on the final state, but I'm writing this as an expectation value. Then I have minus, and then I have a term which goes like h of I, and then I have q of E0, and this contains now this constant delta E0. But this delta E0 is a term which I'm now going to set up order by order in the interaction. So if you look back, this is going to be given by the expectation value of the ground state ansatz with the interaction. So the what we have now is a new term here, which is going to be equal to q divided by E0 multiplied with h of I, like this. So if we write it out now, the third order term, and later when we are going to compare with a simple example and Brienne-Wigner perturbation theory, we're also going to look at terms the fourth order. But that's something which we will do a little bit later. And then we have h of I minus, and now I can actually, since this is a constant, I can single out this term here, because that's an integral which I'm going to evaluate, irrespective of what I have here. So this is going to be equal to h of I, and then I'm going to have a q squared, which is equal to q. So I'm going to have E0 squared multiplied with h of I, and this is then multiplied with the expectation value to first order of the ground state ansatz, with respect to the ground state ansatz, sorry. Now, this is something which you should just note now, because this is going to give rise to terms which will have an unphysical interpretation, and they will be cancelled by other terms, and we are coming back to that one. That leads to something which is called Pauli violating diagrams. And at the end, we are just going to have something which is called a summation over only linked contributions. We haven't defined this yet, but we will wait a little bit till next week. But now we're just going to go through what these terms can mean and how we are going to relate them to full configuration interaction theory. We're also going to start to look at a diagrammatic representation of these terms. So let's now assume that we want to look at many-body perturbation theory to second order. This is an extremely common approximation in many applications of many-body theory. And this is often written as MBPT2. So that is to second order in the interaction. So let's take a closer look now at what we may get. So if I now look at my expression for the energy, what I will have then, I have actually delta E 0, which is given by epsilon, no, sorry, not epsilon, but the exact energy, E0, minus the non-interacting energy. And this is now given by all these terms in perturbation theory. So I equal 1, and in principle to infinity of delta 0 of I. And now we are simply going to approximate this one, and we will shuffle over to the right-hand side, epsilon 0. So if we now do perturbation theory to second order, our energy is going to be given by this non-interacting energy. And then I'm going to have delta E01. And this is nothing but our old reference energy. Just if you remember what we did long time ago, this is the same as the expectation value of this quantity. And then we have a second order term, plus delta E0 to second order. And now the second order term is the one which we are going to analyze a little bit more. Now, if we look at the first order term, we're also going to bring back some of the diagrammatic representation. So the first order term is something which we have calculated many, many times. So delta E0, 1 here, is given by a sum over all the states below the Fermi level, Ij, and then we have this anti-symmetrized element. So we have these integrals. One is a direct term and the other one is the exchange term. So what we have in this specific case is something which we can then rewrite. So if we look at these terms, 1/2, and let's set them up here now. So we would have the direct term. This is one integral. And then we have the exchange term where we have Ji and V of Ij. Now, the common way to deal with this now, if you think of this as whole states, so that means that what we would have, and this is just a reminder of what we did earlier. So we could write this as a diagram for the direct piece, where we would have an incoming state, and now we're labeling this as whole states. is an instantaneous interaction. So these are the incoming Hall states, I and J. And then we have an outgoing term, which is also given by I and J. And then we are putting a plus sign here. But then from the way we set up the lines here, if we have a crossing line, that is going to mean that we have a state where we have now interchanged particle 1 and particle 2. So we have I and J coming out, but then we have this crossing fermion line here. And here we would have the state I, and here we have the state J. And what is normally done then is that when we have a summation of all the states below the Fermi level, we would simply write this out as closed loops, Ij, and then there is a new diagram, which we can then write like this. So this has 0 loops, no, sorry, 1 loop and 2 whole lines. So that gives rise to a minus when we now open it up. So this is I and J. So this is the compact way which we would typically write such a contribution. Now, one of the things which we will be starting with tomorrow is to set up the diagram rules and also look at the mathematics which leads to diagram rules. Because a diagram is a very compact way of representing specific processes. Now we're going to move to the second order term. So the second order term, let's take a closer look at that one. So if I write it out first in its general form without specifying these operators. So we have a phi 0, and then we have this h of I. We have this operator q, and then we have an epsilon 0 minus h0, and then we have h of I multiplied with phi 0. Now, this term, when we write it out now, in terms of those states which are not included in the model space, this is the same as writing this as a sum of a lambda equal to 1 to infinity in principle. And then we have a state here, which is phi 0. We have h of I, and this is now acting on this intermediate state, phi lambda, which in our case can be a particle hole excitation, etc., different types of these excitations of phi 0. And this is divided by epsilon 0. But now what we have is an epsilon lambda here, because when we look at the denominator, what we have is that this operator acting on an intermediate state, and that is given by epsilon lambda times this intermediate state. So remember now that all these states which we have chosen are eigenstates of the non-interacting Hamiltonian. And when we look at that denominator here, what we have is simply, if we now make a Taylor expansion, this is going to act on the states, the phi lambda. And if we then rewrite it as a denominator here, we get simply epsilon 0 minus epsilon lambda. So this is the term, which we now are going to dissect a little bit, depending on the type of intermediate states which we have. So let's look a little bit closer now. So keep in mind that these states, the way everything is written here, these are many-body states. Now, if you think back to what we have done with the FCI calculations, in the FCI calculations, we got terms like this, but we didn't have this denominator, and we didn't have this interaction which you see here. Now, what we're going to do now is simply to link this term and that term to those coefficients which we got from the full configuration interaction theory calculation. So let's look at the expressions which we're going to deal with. So we are going to have to calculate something which looks like this, lambda, and then we have the interaction Hamiltonian, and phi 0. So we are going to assume that this interaction is at most a two-body interaction. That means for us, and this goes back to one of the exercises we had in the very beginning of the semester, which led to what are called the Condon-Slater rules. What we found then is that the only non-zero contributions, since lambda is always different from 0, is that phi lambda can be equal to a one particle, one hole excitation. So that is a one particle, one hole, or it can be a two particle, two hole excitation. Those were the only terms which we found earlier when we looked at the FCI equation, which would contribute. So these are actually the only possibilities which we have. If we now look at the Hamiltonian which we have, and we look at the Hamiltonian with respect, normalized with respect to a new basis, we have to be a little bit careful, because what we have done now is just to single out the interaction part of the Hamiltonian. So let's look at this term when we rewrote the Hamiltonian with respect to a new vacuum state. So what we did earlier in the semester was to take H0 plus H of I, which is equal to a Hamiltonian. We rewrote that in terms of with respect to a new vacuum state, with respect to phi 0. What we got then was that H, sorry, this should not be H0, this is the full Hamiltonian. What we could do then was to actually rewrite this one in terms of the reference energy plus an operator F of n plus an operator which is just the two-body part. Now, the F of n part is a part which also contains something which enters into the reference energy in perturbation theory, because what we have done is actually to single out that one body part. So this term here is now, this operator is a sum of a P and Q, and then we have a term here which led to H0, but H0 is something which we now have included in the non-interacting energy. So we would have this one plus what we call the Hjorth-Jensen term times Q multiplied with AP dagger AQ. Okay, so the piece which we are interested in then is actually the Hjorth-Jensen term. So the Hjorth-Jensen, as we labeled it, with an with a superscript. So that as an operator, HF is then given by the summation over P and Q. And then we had this specific guy here, Hjorth-Jensen. And then we had Q, and then we had AP dagger, AQ, which again is the same as a summation over P and Q. And then I have my operator, AP dagger, AQ, and then it contains a summation over the states below the Fermi level. And then I have my P and J, V and Q and J anti-symmetrized. So this is a term which we now have to look at more closely. Then, if we look at the interaction piece, the two-body interaction, so this is one part of the Hamiltonian, which we now are going to look at. So we will have this term. So this comes from the two-body interaction with respect to the new vacuum. And then we need to look at this term here. So it means that our term H of I, the way we are going to use it, is going to be given by this Hjorth-Jensen term plus Q of Hjorth-Jensen of Q of AP dagger AQ plus 1 over 4 divided, and now we're using anti-symmetrized matrix elements. So we have AP dagger, AQ dagger, AS, AR, multiplied with the integral of PQ V RS, anti-symmetrized. Okay, so let's now look at the first term here, because the first term is now going to be a term which we have calculated before. So if I now look at a specific element, which we are going to need to calculate, if we go back a little bit here. So one element which we will need to calculate is actually this term here. Now this term comes in here as well. So even though this would sum over different states, at the end, these states, I'm then going to simply set up which contributions are the essential ones. So if we now look at the term, which is given by a Slater determinant of the one particle, one hole case, and then we are going to look at the one body operator. So we are going to have a summation over P and Q. So there's a one body operator, and later we will do the two body operator. And then we are going to have the AP dagger, AQ, and this is going to act on the ground state of the system, and it's multiplied with P of U Hartree-Fock of Q. Now, this IA is a given intermediate state. So phi IA, which we have here, is one of the intermediate states, which we can make intermediate states. In this summation, where we set up Greek letters, and this runs from 1 to infinity, of phi lambda. So as I said, there are only two possibilities if we now follow the Slater rules. So we can have a one particle, one hole state, which then typically would give us a non-zero integral if we have a one body part of the Hamiltonian. If I take the two body part of the Hamiltonian, the two body part will create in principle a two particle, two hole state, which will not match this state here. So what it means is that we are going to get an expectation value here, which is going to contain this term. And when we now set up the contractions, what we will need to do, and now we just pick these specific states here. So we have AP, we've already done this, so I'm just repeating some of the things which we found before. This is nothing but phi 0, and then we have a one particle, one hole state, AA, and then AP dagger, AQ, acting on phi 0. So this is all defined with respect to the new reference state, which is phi 0. And then we know that, or we found earlier, that the only contractions which are possible is that since A is a particle state, that's this one, and since I is a whole state, it's that one. So that gives us simply delta P A and delta Q I. So this means that when I now go back and look at these specific contributions, what we are going to get then is now a summation over intermediate particle hole states. So this lambda here reduces to a summation over one state A, a particle state, and a state I, a whole state. So what I will get then, when I look at that specific contribution, so this is just one of the possibilities which we have. So the one particle, one hole term gives to second order in the interaction. It's going to give us a summation over AI. So AI is now the set of states lambda of a one particle, one hole type. And I'm going to get one term, which is I, and then I have my U Hartree-Fock, and then I have my state A, and then I have A, and then I have my U Hartree-Fock, I, and then I have to subtract from this one epsilon 0 minus epsilon IA. And now we remember that this epsilon IA is the same as the particle energy minus the whole energy, because we're taking out the whole, plus epsilon 0. So if I plug that in, I can actually write this equation in a more compact way, which is going to be given by the difference between the Hall energy and the particle energy for this specific state defined by a one particle, one Hall excitation, where the particle is in the state A and the Hall is in state I. And just keep in mind that in principle, A runs over an infinity of single particle states, whereas I is limited by the states up to the Fermi level. But in principle, we always truncate the summation over A. But if we now collect everything, what we will get is something which looks like this. So I'm going to have a summation of AI, and now I can simply use the fact that these are also emission operators. So I have U of Hartree-Fock of I squared divided by epsilon I minus epsilon A. And these are now single particle energies. I write this as a SP, single particle energies. So what I've done here is actually to go from a representation where I looked at many body states. So I just want to have you with me on this way of thinking. If you go back a little bit, so what we did here, if we look at the expressions, this is a many body state, this is a many body state. Now, due to the fact that these many body states are built up as products of single particle states, either through a Slater determinant or through a permanent, if we're looking at the bosons, that means that we can break everything down into single particle terms only. So this is the result of an set of overlaps to second order interaction for many body states. Now, if I now plug in the expression for U Hartree-Fock, this is going to be given by a sum over Aij, and then I'm going to have these matrix elements, so which are actually given by integrals. So I will have A of J, and then I'm going to have the anti-symmetrized matrix element, and I'm going to have my I and J, anti-symmetrized squared, divided by epsilon I minus epsilon A. This is the final expression. Now let's take a closer look at this. And if we now bring back the FCI term, because now it becomes interesting, FCI term for F of n. What we had then, when we look at the FCI term, is something which ended up looking like this. So we had then a sum over A and I, and then we had the coefficient CIA multiplied with A, and then we have this operator I, like this. Now, this F contains also the non-interacting piece, which we have shuffled over in the definition of the correlation energy. But if you look at the expression which we have for many-body perturbation theory, so here we also have H0 plus U Hartree-Fock. Here we have only U Hartree-Fock. So what we are doing now, if we now want to look at these equations, we can now, if we take this term, the first term, so we're going to have something which looks like A. If we now just write it again in terms of the U Hartree-Fock term, so we are going to get a term which goes like I of U Hartree-Fock of A multiplied with A of U Hartree-Fock. So let's just leave out the term with the summation over J. And now I'm writing it like this, of epsilon I minus epsilon A. So this is many-body perturbation theory to second order. If I look at my FCI calculation, what I have then, so this is MBPT to second order. And the FCI term is a CIA. And here I would have the I of H0 times A plus the I of Hjorth-Jensen of A, like that. Now, what we often do now is that we assume that H0 multiplied with A, this could be now, if we assume that, this could be an eigenstate of H0. If we assume that, then this term is going to be equal to 0. So that becomes equal to 0. And if that is an assumption which you have made due to orthogonality, because then AI is actually going to be equal to 0 because A is going to be different from I. In that specific case, this summation which we have becomes equal to AI. I have this coefficient CIA, and then this is multiplied with, actually I should have had inverted A and I here. So here it's actually A, and this should be I. So let's just do that, sorry. Now, what we see now is that in many-body perturbation theory, in NBPT to second order, for the one particle, one whole term, what we see now is that CIA is equal to this term I, Hjorth-Jensen, and this is something which we can calculate. And we will see that when we go to higher orders, we can calculate these terms with elements here, which are all known. So this term which you see here can be calculated. We know how to calculate the integral, and often this would just be something which we put in a table. Similarly, this is a term which we can calculate. We know these ones because we have often assumed that we know how to solve this problem. So this means simply now that what we can do here is now to set up a expression order by order, and every order in perturbation theory is now going to give me an approximation to this term here. Now, when I diagonalize, then I have the exact term, which means that this one from FCI will contain terms in many-body perturbation theory to infinite order. So if I go to third order now, I will find a new expression for this term, which I can bake in and express these coefficients, and so on and so on. So when you diagonalize, you're actually calculating these terms in perturbation theory to infinite order. Now, if I truncate this order by order, like we've been doing here now with many-body perturbation theory to second order, then you see that we have a very precise recipe which allows us to approximate the coefficients we would get from FCI. So if we now want to summarize a little bit what we are doing here, is that many-body perturbation theory with Rayleigh-Schrödinger perturbation theory allows us, order by order in the expansion, in terms of the interaction, it allows us to calculate an approximation to the coefficients which we would get from FCI. So clearly, if you can do an FCI calculation, you have solved the problem. However, since the number of single particle states, as those which you see here, is in principle running from, for A, from a certain state above the Fermi level to infinity, it means that we have an infinity of these determinants. So the hope then, when you do many-body perturbation theory, is that it's easier to make an approximation of this sum here than to make the calculation in a full basis of Slater determinants. So when you do an FCI calculation, you have to set up all the Slater determinants. When you do many-body perturbation theory, you're simply rewriting everything in terms of a sum of a single particle states. And that hopefully is something which is more doable when we now are going to make approximations. So I hope you see the basic philosophy here. And tomorrow we are going to calculate the term which comes from the two-body interaction, and we are going to link that also with the expression which we found earlier from FCI. So when we did FCI, what we had is a similar term. So let me see where I put it. I think we did this in the very beginning of the lecture today. So when we put up FCI calculations, so let's just go back. So in the FCI calculation, what we had is a term like this from the two-body part of the Hamiltonian. The one-body part of the Hamiltonian gave us this. And this is a way by which we can now actually construct the terms order by order. And tomorrow we're actually going to calculate this term and see what that one looks like. And many-body perturbation theory will then give us a recipe by which we can calculate correction to these terms order by order. The hope is clearly that the expansion shows sign of convergence when we reach a certain order. That means that we can truncate the expansion, let's say to third order, or even, hopefully, to second order in the interaction. So tomorrow, we are going to evaluate this term in many-body perturbation theory. And what we're also going to do is to set up diagram groups, which will give us a very compact way of analyzing and setting up the final analytical expressions. So we are going to get analytical expressions for these components in terms of quantities which are all known and we know how to calculate them.